Good afternoon, Professor.
Hello, hi, good afternoon, Dr.
Yeah,
Siddhi.
I'm Sudha.
Yeah, nice to meet you.
Well, nice to meet you. Welcome to SRM ISD,
Thank you.
Ramapuram campus. Thank you so much for joining this meeting.
It's my pleasure.
Thank you so much.
Can I just check my
Yeah, please.
slides whether they are getting shared properly? Or you have to give me the sharing right? So you have to make me co-host or something?
Yeah. Madam?
Yes, sir. Yes, ma'am. Yes.
There's a feedback from this
Madam?
one particular.
Madam, please mute mic, ma'am.
I think you can also mute as a host. You can mute anybody.
Yes, sir. We have the control.
So I still don't have the sharing. I still disabled it.
Yes. Subramanian, sir?
Sir, I have given you as co-host, sir. Now you can share, sir.
Oh yeah, now I can. Okay. Do you see my screen?
Yes, sir. Your screen is visible.
Okay, let me just make it to the.
Yeah, you are audible. Your screen is visible. Madam Jayalakshmi, ma'am, mute all, ma'am.
Okay, ma'am.
Is it okay?
Yes, sir.
All right. So I will now unshare it, or
Please unshare, sir.
yeah.
Thank you, sir.
So dear participants, soon we are going to start our 2-week FDP.
Professor, you're all working from home or going to university? Madam, unmute his mic, ma'am.
Oh, yeah. We are in university. We have university has started, so we can go and take the classes if the class size is less than 50 students with 1 meter distance between the students.
But still you don't allow international travelers.
Yeah,
Other
international
than those
travelers
holding
have-
PR.
Yeah, except that's right.
So many friends and relatives are held up due to that.
That's true. That's very true.
My friend's daughter delivered a baby without her mother and mother-in-law.
Oh, yeah. Many people are facing lots of problems. I also cannot go to India, because of this. Because when you
But
come
you
back,
can
we
come
have to
and go, no? You can stay there. You have to stay there 2 weeks in the hotel.
Yes, we have to do the quarantine. Yeah.
Ma'am, shall we?
Vaccination is also compulsory, sir.
Sorry.
Vaccination.
Yes, it's not compulsory, but most of the people have taken it. So we have about 81% and who have taken 2 doses. Yeah.
Here in our university, they made it compulsory.
Oh, okay. Here, if you are coming and taking the classes in person, face to face, it is compulsory for the staff, unless there is a medical reason, because some people have some medical issues.
Yes.
So university, I think it's about 99% people have the vaccination.
Oh. Some are afraid to take.
Yeah, that's the particularly very old age, and some people who have some particular beliefs, they are not taking it.
Even youngsters, the few youngsters are not willing to take. They think that it is for them only. They don't understand that they are taking the vaccine not only for themselves, for others.
That's true.
Very good morning, Professor. I am Dr. Subramanian. Sorry.
Hello, Dr. Subramanian. Yeah. How are you?
Yeah, fine. Due to some network issue, I couldn't join. So that. Welcome, sir.
Oh, thank you, thank you. So are we waiting some more or are we going to start soon?
Ma'am, shall
Dean, sir. Our Dean,
Oh, okay, okay.
just a minute.
Ma'am, shall we start, ma'am?
Jayalakshmi, ma'am.
Ma'am?
Dean is joining, just check.
Okay. Join. Yeah, ma'am, he joined, ma'am. Good morning,
Good morning,
sir.
Dean. Yes. Madam, please start.
Okay. Good morning to all. Morning is God's way of saying one more time, go, live life, make a difference, touch one's heart, encourage one's mind, and inquire one's soul. I welcome you all for the 2-week organized by FDP on Advanced Computational and Experimental Research in Physics 2021, organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram Campus, Chennai. SRM Institute of Science and Technology is one of the top-ranking universities in India with over 38,000 students and 2,600 faculties across all the campus, offering a wide range of undergraduate, postgraduate, and doctoral programs in engineering, management, medicines, and health sciences, and science and humanities. Institute has academic tie-up with leading foreign universities like MIT, University of California, USA, and University of Dundee, Oxford University, UK. Our institute is accredited by NAC with A++ grade in the year 2018 and got placed in A category by MHRD. Like in the morning, prayer is the key that opens to us the treasure of God's mercies and blessings. Now I request you all to join for Tamil Thai Vaalthu.
நீங்காரும் கடலுடுத்த நிலமடந்தை எழிலொழுகும்
5 minutes.
மதனமென நிகழ்வரத கண்டமிதில் எக்கணமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பேரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Now I request our HOD, Department of Physics, to welcome the gathering. Ma'am.
Respected Dean sir, good morning sir. Since our Dean has got one more program, I request Dean to give his address. Sir.
Yes, madam. Thank you. A very good morning to everybody present here in this today's online session. Honorable Chief Guest for today's program, Dr. Rajdeep Singh Rawat sir, Professor and Head, Department of Natural Sciences and Science Education, NIAG Technology University, Singapore. The other speakers for this 2 days faculty development program and the convener of this 2 weeks program, Dr. Sudha Madam, and the faculty members of Department of Physics, participants, a very good morning to everybody present here in this online session on the occasion of FDP program. I'll appreciate the department has taken the 2-week international faculty development program on advanced computational and experimental research in physics. In fact, I'll appreciate them because the madam when was telling, I really wonder that 2 weeks of program organizing a physics department and bringing eminent persons from the entire, all the countries, about more than 15 the eminent personalities have been joining on session wise and day wise and talking about the important about the research, experimental research in physics. You know, when we say that actually the 2 weeks program is there and obviously there will be a more content will be there. This is very, very essential and useful to the people, not only for the physics, the entire the teaching community has to utilize these resources. In general, in computational physics, you may learn to use up in a computer in a laboratory for solving the advanced problems in the physics. There may be a numerical solution or whatever it may be. This will help us in computational capabilities. I will say that there is a lot of advances in the physics. Now, earlier days, we used to call the physics is meant for only related to the people, those who have been going for BSc, MSc, like this. But now the applications are more in the engineering. Now, without physics, nothing is there in the engineering. I can say that engineering is a part of a not even 1% of the physics. The origin is the physics. Whatever we studied today, maybe a statics, maybe dynamic, maybe forces, everywhere the physics is reflected. Maybe a part of, everything is applications. You take about EC, whatever the transistors, diode, triode, semiconductors, all actually, they have been, everything is an application of physics. The concept is in the physics. So my sincere request to the faculties and the participants, and it's a very great opportunity to have, 2 weeks program. That too, they made it in the, after their working hours. They made very convenient manner in such a way that you can find a little bit free time after having a cup of coffee after the evening, and comfortably you can sit and you can try to learn so many things. I'm also thankful to the technology because of the COVID-19, we are able to, organize so many eminent persons from the various countries on a single platform to know about the technology. See, learning with technology, whether it may be offline or online, will be a same one. I'll appreciate the department as bringing such a eminent person, Dr. Rajdeep Singh Rawat, who has, when I just read about his biodata, he have been studied in a top college, Hansraj College, BSc, MSc means, I will say that is one of the best college in India, got very good ranking. Hansraj College is meant for, sciences always. When I see that, it will be in the top 1 rank in Delhi University. And with the background, that too, you have been working in abroad for more than 19 years in Singapore. I know how much actually sir is having the technology and discipline, etc. बहुत शुक्रिया साहब, आप इधर आने के लिए. Namaskar sir. So I'll appreciate the people, and also I'll be very much interested in this particular topics. You have taken very good topics, and most of the topics also I have been familiar. Say take about the material science, about the energy, and also teaching pedagogy, this yoga, laser technology. You said density functional theory, non-linear dynamics. So these and all actually, in fact, I've been even taking a few subjects also on this. The material science I've been handled many times and all. I know the properties of the material, etc. But however, I want to learn so many things from this workshop. I must be very thankful to all the people for giving this opportunity to address particularly to eminent persons. And after this session, I'll be very much interested to join. And I'm very happy. And after 4:30, 5 o'clock, I'll find a little bit entirely free. I'll be there in my office. Definitely, I will attend all the sessions. I must be very thankful to the organizers and the coordinators for giving this opportunity. I can say that the Department of Physics is a big competitor for the even engineering departments. So I thought of actually the physics, chemistry, mathematics, English, they may support the engineering department, but now they became very good competitor. They're able to, organize as much as more than the engineering departments. So that shows that department strength. I'll appreciate the department staff members also. They have been very good in organizing these programs like in international conferences and FDP programs. Thank you one and all. Thank you, madam, for giving this opportunity. I wish you all the best for this entire session of this FDP program. Thank you. Thank you very much.
Thank you very much, sir, for your kind words of appreciation. In spite of your busy schedule, sir has come here to wish us. Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you, sir, for your encouraging words. Now I request our HOD, Department of Physics, to welcome the gathering. Ma'am.
Yes. Good morning, everyone who have joined this inaugural session of 2-week International Faculty Development Program on Advances in Computational and Experimental Research in Physics, organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram campus, from 13th to 25th September through online platform Zoom and also live stream through YouTube. I take privilege in welcoming our chief guest, who is a stalwart, Professor Dr. Rajdeep Singh Rawat, Professor and Head, Department of Natural Sciences, and Science Education, Nanyang Technological University, Singapore, who had at the first instance accepted our invitation to deliver the inaugural and keynote address. He is also going to enlighten us on plasma processing as a novel tool for high performance electrode material synthesis for energy storage and conversion devices. And Dr. Rajit Singh is a luminary in material synthesis for energy storage devices. We are gifted and blessed to listen to the world-renowned person today. Thank you very much, Professor, for sparing your precious time with us this morning and afternoon for you. His accomplishments is quite long. I request my colleague to share his achievements. I extend a very warm welcome to the faculty members and research scholars from universities, institutes, and colleges. We would like to extend our gratitude to the other eminent speakers of 2-week International FDP. The lecture series covers wide range such as X-ray photo, electron spectroscopy, crystal growth, nanotechnology, space science, green energy, biophysics, laser, thin films, piezoelectric materials, molecular dynamics simulation. The Department of Physics is recognized as a research department. Research scholars are pursuing their PhD program. The faculty members are actively engaged in cutting-edge research in the frontier areas of engineering, science, and nanotechnology. In the last 5 years, more than 100 papers have been published by the department in the journals of international repute of high impact factor. The department has 4 research projects funded by Department of Science and Technology, Science Engineering Research Board, and SRM Management. Active research is being carried out in the field of X-ray crystallography, crystallographic studies on drug molecules, dielectric studies, crystal growth, electronic structure of materials, nanomaterials, and ceramic compounds. Every year, the department is conducting national conference on hierarchically structured materials. And last February, we conducted international conference on hierarchically structured materials, workshop on material characterization, faculty development program, and mini project contest for the benefit of faculty, research scholars, and students. Thank you and have an enjoyable time of learning.
Thank you, ma'am. Now I request Dr. K. Subramaniam, Assistant Professor, Department of Physics, to introduce our chief guest. Sir.
Vijay, ma'am, am I audible to you?
Yes, sir.
Good morning to one and all present here. I feel very proud to introduce one of the eminent personality from the prestigious institution, Dr. Rajdeep Singh Rawat, Professor and Head, Department of Natural Sciences and Science Education, Nanyang Technological University, Singapore. Dr. Rajdeep Singh Rawat has completed his UG in University of Delhi, MSc Physics from University of Delhi. He has completed his PhD in Experimental Plasma Physics from University of Delhi in the year of 1993. He has worked as a lecturer and senior lecturer in University of Delhi till the year of 2000. Later, he has joined in Nanyang Technological University, Singapore as a professor in physics in the year of 2002. His main research interest involves performing fundamental studies on pulsed plasma devices such as dense plasma focus and their application, variety of ways such as neutron source for novel material testing, for first wall of fusion reactor and explosive material detection, radioisotope synthesis, soft X-ray lithography, soft and hard X-ray imaging, material modification, and nanostructured material synthesis. He has extensive experience in various basic plasma and nuclear diagnostic techniques. His current research focus is graphene and transition metal nitrides, oxides based 3D porous nanostructure hybrid assemblies. He has published more than 240 journal papers and over 70 conference papers with greater than 6,500
Ma'am, not audible.
Hello, sir, Subramanian sir.
Sir, Subramaniam sir, you are not audible, sir. Subramaniam sir.
Really, I am very proud to be having Dr. Rajdeep Singh sir as a chief guest for this inaugural of 2 weeks FDP program. I hand over the session to Dr. Rajdeep Singh Rawat sir. Sir, please take the session, sir.
Okay, good morning. First of all, thank you. Thank you, Dr. Subramaniam, for contacting me through Dr. Shrikant and giving me this opportunity to give this inaugural keynote talk for this wonderful program in advanced computational and experimental research in physics, which is for the faculty development program. And I was surprised to know about the numbers that I was told that, I mean, it's a huge program, and there are not only many distinguished speakers, but there are a large number of participants, which are not only the faculty, but the student researchers and students as well. So this is something fantastic, and I think it provides a platform to the researchers where they can hear from some experts in the field. So let me now share my screen. Is my screen shared?
Yes, sir.
Okay,
Sir,
I'll make it full screen.
To full screen, sir.
Yeah,
Full
I'm
screen.
doing that. Yeah, I'm doing that. Okay, I will change the setting.
Yes, sir.
Okay, is it okay now?
Yes. Yes, sir.
All right. So thank you very much, Dr. Subramaniam, for introducing me in great detail. And I'll just therefore continue on the work that I'm going to present over here. Once again, I'm Rajdeep from Nanyang Technological University. This is the university. Sorry. Yeah, this is the university where I work in. And I basically work in an institute called National Institute of Education, which is an autonomous institute of NTU. And we basically train teachers for Singapore school system. You know, in Singapore, we have about 33,000 school teachers, right from the primary to the junior college. So every one of them, they have to go through my institute. So in my institute, basically, the main area of focus is actually education and education research. But then there are people who do content work as well. So I'm one of the content, you can say, content expert as well as, teaching over here. So the work that I'm going to discuss today, it was already highlighted what I'm going to talk about. But let me just try to give a brief overview of what it is going to be about. The focus of the work today is basically the electrode material synthesis for energy storage and conversion devices. So what do I mean by energy storage devices or energy conversion devices? Energy storage devices over here is basically referring to the lithium-ion batteries and sodium-ion batteries. We know that these are basically the devices which are used by everyone. Every one of us is carrying a handphone in our pocket, and they are using these lithium-ion batteries or new technologies that are being developed. Whereas the energy conversion devices are basically over here is referring to the devices which can be used to convert one kind of fuel to another kind of fuel, or one kind of materials. For example, over here, I will be talking about a generation of oxygen and hydrogen from water by water electrolysis. So basically, it's about the electrocatalysis. So work that I'm going to discuss today is basically the one which is done by my PhD student, Dr. Bo Oyang. He has graduated and he worked with me for 1 year as a research fellow, and then now he's an associate professor in Nanjing University of Science and Technology under 1000 talent program in China. And this was done in collaboration with another PhD student who is also graduated, Dr. Chang Yongchi, who was the PhD student of Professor Fan Hongin, my main collaborator in this. So this work actually initiated, we started doing it only very recently, only 5 year, and it was initiated with the help of Professor Mohan Jacob from Australia, who visited us for about 4 months to do some, on his sabbatical to do some collaborative research. And that is how it all started. And I'm very surprised as well as very, thankful to him that we in last 5 years, we have done some good work in this direction, which I'm going to highlight. Not all of it, but at least some of it. So this is an overview of my university, which is basically one of the 15 most beautiful campuses in the world. Singapore is a very small country, only about 700 square kilometers in size. So we are in the western part of Singapore, just opposite to the airport. And this is a very, not very huge, but a very beautiful campus. And some credentials about our university. It's quite a young university, actually was established only in 1991. So it's almost only about 30-year-old. And we have been doing quite well, and our rankings have been improving. And currently we rank around 12th in university QS ranking. And it is basically #1 university in the young universities, which are formed in the last 50 years for last 5 years consecutively. As far as the student numbers are concerned, which is mentioned over here, so we are also, total student strength is somewhere around 35,000. So it is something similar to the your student number that was just mentioned. But we are pretty international university in the sense that we have students from about 92 countries. And we have also faculty members who are also from 81 countries, as you can see over here. As far as our group is concerned, basically we call our lab as the Plasma Engineering and Applied Research Lab, PEARL. And 3 of us basically work in this lab, myself, my colleague, Prof. Polly, and Prof. Stewart. Prof. Stewart is an expert in nuclear diagnostics, whereas my colleague Polly is expert in laser and pinch plasmas. I work on basically on pinch plasmas as well as laser produced plasmas. So initially when I joined over here, actually this lab itself was formed in 1991. So it is also the same age as the age of the university. And the initial focus of our research lab was basically on this dense plasma focus device, which is still the focus. It's a non-cylindrical Z-pinch device where you can produce a very high temperature, high density plasma. And it is the same device on which I did my PhD in University of Delhi under Professor Srivastava. And this device, because it produces very high temperature and high density plasma, it actually acts like a source of many different interesting radiation and particles. For example, we can get neutrons. That means you can have fusion going inside this device and you can produce fusion neutrons. And it also produces very high energy charged particles, ions basically of mega electron volt range. And we can also get relativistic electrons. And we also get, because of the high temperature, high energy X-rays. So we have used this device for very different fundamental studies in terms of plasma dynamics, plasma instabilities, plasma turbulences, and also have used these various components for various different applications, which were highlighted by Dr. Subramanian just now. Our other field is basically in the laser plasmas, where we do laser plasma interaction and fundamental laser plasma interaction experiments using different diagnostics, plasma diagnostics. But later on, as I mentioned, that the Singapore actually focuses more on the applied research. We started using both these devices basically for application area for material processing and synthesis. And as I mentioned that for last 5 years or so, we have started to work on the low temperature plasmas. These are high temperature plasma, these are high temperature plasma, these one, but these are the low temperature plasmas. So these are low temperature and these are the high temperature plasmas. And in this, basically, we started working on this using this low temperature RF discharge based plasmas for material processing and synthesis. And so what I'm going to talk today is only about this work. And so our group has been pretty successful. We have received a grant over about 15 million, which in Indian rupees is about like 75 crores over this last 20 years. I joined over here. We have graduated good number of PhD students, and we get large number of overseas visiting students also, which basically are registered as a PhD student in their own university, and then they come here for some like 6-month or longer program or even shorter program for as a non-graduating student, and then we do some collaborative work. So there is a program called NTU India program, which is led by Professor Chaudhary, and there are several students. I think they come not only to NTU but different institutes, different schools of NTU under such programs. So if there are students over here, they can explore about that program, and that will give them the chance to come over here, where they are basically supported by their university as well as by NTU. So today's talk, basically, I'm going to focus on this, as I mentioned, the energy storage and conversion devices. So I'm going to give some introduction to the necessity of it, basically the shifting towards the hydrogen economy for the conversion devices, and then about some energy storage in terms of the lithium and sodium ion storage batteries, and the role of plasmas in these nanomaterials processing and synthesis. And then I'm going to cite some examples of the work that we have done using low temperature carbon plasmas. I will not get the time because I don't want to, make a very fast presentation. So I will not concentrate on the nitrogen plasma. I will not highlight that too much. And finally, I will conclude. There is some background noise. May I request people to mute themselves?
Jayalakshmi ma'am, please mute ma'am.
Yeah.
Unmute the madam. Unmute the chief guest. Subramanian sir.
I'm unmuted, I think. Can you hear me?
Yeah. We can hear you, sir. Please.
Okay. All right. So as far as the energy conversion is concerned, I'm going to talk about this water electrolysis. So as we know that we are living right now in what is called as the carbon economy, and everybody knows when I say living in carbon economy, because basically our main energy resource, still the 85% of it comes from the fossil fuels in terms of the energy that is generated by coal, or basically using the natural gases and oil. So 85% of our reliance is still on fossil fuels, but the problem is that it generates carbon, and we all know what the problems are. Even this year, there is a lot of extreme weathers, from drought to very heavy rains, and even the fires and the temperature going into the extreme directions. And all this is because of the increasing carbon content in the atmosphere. So everybody is trying to reduce this carbon footprint. And one of the way to find an alternative, energy alternative compared to carbon is to shift towards what is called as the hydrogen economy. That means you use hydrogen as a fuel. And that is very much possible because hydrogen in the presence of oxygen basically will get converted into water, and along with the release of heat and work. So that means the useful things can be obtained from it. And therefore it is quite suitable to replace the carbon economy. Of course, right now it is quite costly, so it is not replacing it, but this is the increase of hydrogen is on increase. I mean, the use of hydrogen is on increase. So there are several aspects of hydrogen economy. You have to produce the hydrogen before you can use it. And of course, there are many other factors that are involved. You have to package it, you have to distribute it, you have to store it, and then you have to transfer it. So if you look at the hydrogen production, there are several ways of producing it. And hydrogen production itself has become quite big. For example, even at this stage, I think it has crossed over $100 billion, the economy, in terms of its size. But 95% of this hydrogen production is coming from two sources, which is basically from the coal gasification or from the steam reforming of natural gases. So you see these two, which are contributing to about 95% of the hydrogen production these days, are not good source, because then you are still depending on fossil fuels, because you are still using coal and the natural gas. So basically you are not helping in a way to reduce the carbon footprint. So what is the best alternative? So US Agency for Energy, they have recognized that within next 50 years, not 50 years anymore, within next 30 years, that means by 2050, we have to reduce this dependence on these two processes by increasing the output from what is called as the water electrolysis. So water electrolysis, I will explain what it is. So basically over here, you are using water as a source for hydrogen as well as oxygen. So in water electrolysis, which I think most of us, we all know that if you just simply take a water and insert a pair of electrode over there and connect it to a power source, so at the positively charged anode, what happens that we can get an oxidation reaction going on, which is listed over here. And that basically breaks down the water, and by oxidation process releases oxygen over here. So what is happening is what we call as the OER reaction is taking over here, oxygen evolution reaction. And it is not only the oxygen being evolved over there, but also there are 4 hydrogen cations that are produced, which are moving inside the water from the this positive anode to the negative cathode side. Whereas these electrons which are generated in this oxidation process, they move through the outer circuit. And then they again recombine at this electrode, the so-called cathode over here. And then this reaction goes over here, which results in the hydrogen production. So the amount of voltage that is required to carry out this reaction is, according to the thermodynamic calculation, is basically about 1.23 volt at 25 degrees centigrade. But that is what the theory says. In reality, when you do the experiments, it's not possible to carry out this electrolysis process at that voltage. And normally you have to apply a slightly higher voltage. And that extra voltage that you apply is called overpotentials. And this overpotential is different for the different electrode materials. Platinum is the best choice because the platinum has the lowest overpotential, typically around 30 to 50 millivolt. And platinum, being a noble metal, is also very, very stable. That means it doesn't degrade, and that's why it is in use. But the point is, or the problem is, that platinum is expensive, it is rare. So people want to find out a solution where this platinum can be replaced by some other alternatives which have lower overpotentials and which also can demonstrate higher stability. And that is where the research focus is. And that is what I will be showing later on as well. As far as the batteries are concerned, if we just look at the sodium ion batteries or the lithium ion batteries, let's talk about in terms of the lithium ion batteries. These batteries basically have four important components. One of it is called as the cathode. Cathode over here is basically made up of the lithium liberating compound. That means these are lithium salts which can liberate the lithium ions during the charging process. So when you have connected your handphone, basically a lithium ion battery, to a charging source after it is drained, what you are actually doing, your lithium salt at cathode is actually liberating lithium ions which flow through the electrolyte. So electrolyte is the medium which allow this lithium ion transport in a better way. And then they go towards what is called as the anode. And this anode material is somewhere where the lithium, you can say, is stored. So lithium ions are stored over here. That is what happens in the lithium ion battery. And when you want to use it, that means when you connect this battery to the external load, then these lithium ions, they go back from the anode to cathode. And when they are going back from cathode to anode to cathode in the lithium ions, the electron flow takes place in the outer circuit, and that's how it works. So the performance of the lithium ion battery basically depends on how high is the potential of this anode material to store the lithium ions, how many of them they can store, how effectively, and what is the charge transport, how fast these lithium ions can be transported between these two electrodes. So these two are very important factors, and that is what the people try to work on. So there are different mechanisms by which the lithium can be stored in this anode material. So lithium are stored in this anode material. This is anode material over here. And there are different mechanisms which are called as the insertion, alloying, or the conversion mechanism. Just to understand in a simple way, I will just concentrate on the first two because that is what we have focused on. So in insertion one, what happens is like what is listed over here. You normally use the anode material as transition metal oxide or graphites. This is basically a two-dimensional layered structures, or you can also use the 3D network structures. In this case, the lithium just goes into the lattice without destroying the lattice structure. It just gets intercalated over here and it gets stored over there. And then this is during the charging process, and during the discharging process, it goes back. So some of the material which are used for this insertion mechanism are the one which are listed over here. The number one, which is listed over here, refers to the type 1 mechanism. And what you see over here, the typical, for example, if we take the case of carbon, carbon provides us the capacity of these kinds of battery, theoretical capacity, about 372 milliampere of current for an hour from 1 gram of the material. And these materials, insertion mechanism, you see the size of this is similar to the size of this. That means the size of the anode material does not change much. And that is also seen in this, the table over here. The relative increase is only 12%, 4%, 1%. The size of the electrode material doesn't increase much. But these materials typically have low storage capacity. Now there is another type of mechanism which is called as the alloying mechanism. And in alloying mechanism, as you see over here, the electrode material swells. That means its volume increases by a great amount. And why it is happening so? First of all, for this alloying mechanism, basically you can use metals like tin, zinc, cadmium, or you can use elements like silicon and antimony. So for example, this column over here, number 7, shows the silicon as the alloying material. And you can see over here the difference between the silicon and the carbon. While for carbon, which is using the type 1 mechanism, there is only one lithium ion is, you can say, absorbed for 6 carbon atom, it's LiC6. Whereas for silicon, it is Si Li 4.4. That means for every single silicon, there are 4.4. So this is like almost like 24 to 30 times bigger than that. So there are a lot many lithium ions that can go into that site. And that is the reason why this material swells up. So over here, the volume expansion is like 400%, whereas there was only 12% increase. And since there are lots of lithium that can be absorbed by this alloying mechanism, you can see that the theoretical capacity is actually very high. This is only the theoretical capacity. Experimentally, you don't get that. But theoretically, you can see there is one order of increase in the magnitude of the capacity of these kind of batteries. So while there is a huge increase in the capacity of the material,
you have to do some small calculation.
can you please mute it?
You don't know how to take grading.
So this battery has the huge increase in the capacity, but the problem comes from this expansion, the volume expansion of this electrode material. When this electrode material expands so much so that it gets ruptured, we call it pulverized, it gets pulverized. So the structural integrity of the electrodes now comes under question. And also because since it pulverizes, its cycling stability is poor. That means you see nowadays, when you buy a phone, the battery will last 2-3 years and you are doing charging almost every day or every other day. So industry standard is that you should be able to have about 1,000 times you can cycle it, charging and discharging with not appreciable decrease in the capacity. But this pulverization actually limits the life cycle of that. That's what the problem is. So now with this as a background, I will try to highlight some of the things that we are trying to do. So we are trying to do, this battery related work or electrocatalysis related work. When people are making these electrodes, they are basically using wet chemical approach. And it is not a single step process. Some of them are multiple step processes. And most of these chemicals normally use them in larger quantities, and many of them are environmentally hazardous. That's the problem. That's the limitation of these techniques. What we are trying to do, we are now trying to use plasma-based approaches to replace at least a part of this, process. It's not totally plasma-based, but we are trying to go for a hybrid approach where some part of it is still chemical, but wherever possible, we try to use bring in plasmas to reduce the dependence on the pure chemical process. So what is the advantage of this? Advantage is that you use less chemicals. You use a process which provides, a much faster way of doing the things, and I will highlight that later on. And currently the chemical methods, when they use this transition metal oxide, nitrides, and sulfides, many of them, they have limited conductivity. So charge transport is also another important, criteria which is required for this catalytic work or for this battery related work. So this limited conductivity needs to be enhanced. So we are using plasma-based functionalization as well as the plasma-based some other nanocomposite formation so that we can enhance the conductivity. And also we want to have the better stability in terms that we want to avoid or minimize the capacity fading as much as possible. Now, as far as the plasmas are concerned, there are basically two types of plasmas. The so-called, what we call as the thermal plasmas. Thermal plasmas are those plasmas where plasma is basically in equilibrium. The components of plasma in equilibrium. And plasmas have component like what? It has electrons, it has ions, and it has neutrals, the background gas. So for thermal plasmas, all these three components, they are basically in equilibrium. That means the electron temperature is same as that of the ion temperature, is same as that of the gas temperature, or something like that. So because of this, what happens is that this kind of thermal plasmas actually are not so good for the nanostructuring or the work where we want to use it for the nanotechnology, basically because this plasma actually cause the overall heating of not only the surface but also the bulk of the material, because the bulk temperature also reaches the same temperature as the surface temperature. So it leads to the melting, and even because the temperature is very high, the agglomeration takes place, and that actually spoils your nanostructures. But if we use low temperature plasma or the non-thermal plasmas, which are also called as the cold plasmas, then in this case, the ion temperature is basically same as the gas temperature, which is typically around the room temperature, whereas the electron temperature is the one which is very high. So electrons are at higher temperature, but the ion and the neutrals, they are more or less at the room temperature. So what is the advantage? The advantage is that this is like a far from equilibrium chemical factory, which provides us still chemically active species. It provides us ions. It also provides us radicals, or in the excited state, which actually helps us to improve certain things. For example, it provides, as I mentioned, it provides high chemical reactivity, basically because it can provide a better selection of the starting materials. It can provide a better efficiencies compared to the chemical process, and it can also provide higher surface selectivity. That means you can work with many different kind of substrates when you use the plasma-based methods. And in addition to that, as I mentioned, that there is a heating effect is less. That means you can do a much more controlled work in this case of low temperature plasmas as opposed to the high temperature thermal plasmas. But one has to tune these plasma parameters very carefully, because the same plasma, depending on what the plasma parameters are in terms of the density of the plasma or in terms of the temperature of the plasma, it can either cause the deposition of materials, or it can cause the modification, that means functionalization or other things, or it can even cause the sputtering or etching of the material. So somewhere it can cause deposition, somewhere it can cause etching. So you have to tune your plasma parameters in a proper way to achieve what you want to achieve. So in some cases we want to do synthesis, we have to change the plasma parameters. In another cases we want to do the etching or functionalization, then you have to use different plasma parameters. And in order to do that, you have to analyze your plasma parameters. So we do that using different diagnostics like optical emission spectroscopy or Langmuir probes. But over here in this talk, I'm not going to go into the details of this. So what I want to highlight is that even though this work we started quite late, I mean, we started only in 2015. As I mentioned, that we have this Professor Jacob visiting us when we first started using these low temperature plasmas. But in the last 5-6 years, basically through the work of my PhD student, Bo Yang, we published some very high impact factor papers in this field. And we use only two types of plasmas, the carbon plasmas and the nitrogen plasmas. And even in the carbon plasmas and the nitrogen plasmas, when we use them, we actually try to use the sources which are environmentally friendly. What do I mean by that? For nitrogen plasmas, most of the people, they find that the molecular nitrogen, that means N2, which is very cheap and very easy to find, or even if you just use air, you will get 79% of nitrogen over there. But it is very difficult to dissociate it. So people normally don't use the molecular nitrogen when they want to get nitrogen plasma. They use basically ammonia, but then that is toxic, and you have other problems. We simply use only the molecular nitrogen, just this cheap nitrogen cylinder, which are very easy to get, $10 one cylinder, we can get that. And for carbon plasma, most of the people working in graphene and these kind of synthesis, they always will use their favorite precursor is methane. But methane, as you know, is a greenhouse gas, and we don't want to use that. In all our work, we use a sustainable carbon plasma source. Over here, we used what is called as the tea tree oil, and that is what I'm going to start talking about now. So we use this tea tree oil as the source for the carbon precursor. This tea tree oil is used for cosmetic purposes. People know about it. It is used in soaps, and it is used in facial creams and all those things. And it's very cheap source. We bought a bottle which is having a half liter of tea tree oil about 5 years ago from Australia, and we have not even finished half of it. So less than 200 ml we have used. And the method of using it is very simple. We just put it in a flask, and since it has a low flash point, it vaporizes by itself at the room temperature, and the carbon precursor goes inside this. and then we make the discharge, RF discharge, we can get the carbon plasma source over there. And using this, we first demonstrated that we can get vertical graphene within 1 second. Within 1 second, very fast we can deposit the vertical graphene. So once we were able to find out a way of creating this carbon plasma, which could be used for depositing or synthesizing carbon structures, then we started also using it for reducing the material, using the carbon plasma as a reductant, because this source that we are using, actually it is not only the carbon plasma, it is also having oxygen, it has other radicals as well. So many other things are doing those work simultaneously. So now from that initial work, we did many other work in batteries, supercapacitors. So I'm not going to discuss that. So I'm going to highlight just few of the work to highlight that this simple method of getting the carbon plasma using a very simple, setup. The setup that you see over here actually was set up by a class 12th student. He was doing his final year project with me, and the student, and we did very simple thing. We just need to buy a RF generator, and we just used a quartz electrode tube which was connected to a vacuum pump, and then just to use 2 ring electrodes, and we can create the plasma in a very simple way. And with that only, we did all this fantastic work, which we are able to publish in some very high impact factor journals. So the very first work that I'm going to discuss is basically about this. Can I move this? Yeah, I need to move this. Okay, so the very first work I'm going to discuss is about the pre-reduction of the metal oxide using carbon plasma for efficient and stable HER reaction. So what is well known in this community of energy conversion is that transition metal oxides, they are very useful materials because they are very easily available. It's very easy to make them. They go into the variety of nanostructural form, and they have very high specific surface area. But of course, these transition metal oxide, many of them, they show limited electrical conductivity. So that makes the catalytic kinetics quite sluggish, and also many of them has the problem of long-term stability. So just working alone with the transition metal oxide actually does not help. So what people realize that if part of these transition metal oxides can be converted, I mean by reducing them in a metallic part, then this combination of the transition metal oxide towards decorated with metal nanoparticles is a very good way of improving their hydrogen evolution reaction properties. So this paper by Lee et al. In Nature.com, they used the tungsten oxide nanoparticle, and then they used the hydrogen annealing. So hydrogen is a very good reductant, and to convert some of them into tungsten nanoparticle, and then they found that the overall activity is quite improved. But then they did it under the annealing. That means they did it under the heating atmosphere. The temperature used was much higher in order to reduce them. What we have done in this paper, which is listed over here in the small, we use different transition metal oxide like nickel molybdenum oxide, cobalt oxide, and nickel oxide. But focus material was this. We can activate all of them without doing anything. That means we just use them directly as an oxide in a electrocatalysis. And since there is a hydrogen evolution reaction going on, hydrogen is producing by itself. And this hydrogen causes the self-activation, and that actually improves the HER process. But what we found that this was rather not very stable. It was an unstable process. So it helps improve a little bit, but it was not very stable process. So that's why we thought, okay, let's do a pre-reduction. That means we do the reduction of this oxide material by itself. So as I mentioned, we also tried for our own nickel molybdenum oxide nanowires, which were grown by a salvothermal method. We just use the hydrogen annealing for 1 hour under high temperatures, so we can reduce the surface. And of course, it shows the improved HER activities as it is mentioned over there. But as I mentioned that it was unstable even when we did the external pre-reduction using the hydrogen annealing. But when we use the carbon plasma, and notice the timer, only 30 seconds. We used 30 seconds of carbon plasma. We were able to reduce the surface in the nanoparticles, and we got not only the improved HER activity, but we got a very stable structure. And what is the reason for that? Why we got the better stability is something I'm going to explain later on. So this one shows the SEM and TEM images of the material. So the first one is without any plasma treatment, which is basically our nickel molybdenum oxide nanowires, which are grown by on the carbon cloth by the salvothermal method. And then we use with the different plasma treatment. This is 15-second, 30-second, and then this is the 60-second treatment. Just you can notice the time, less than about a minute only. And as you notice that when you treat them with the carbon plasma, we start to see nanoparticle formation over there. These are metal nanoparticles that starts to decorate the surface. And in addition to that, you will notice that on the surface of these nanowires, there is a carbon layer that is getting deposited. So what was happening is that a carbon shell was being formed also. Not only it was reducing the oxide to the metal, but the carbon shell was also being deposited over here. And that is what provided the stability. And that carbon shell can be seen very clearly in these TM images. And you can see those metal nanoparticle structures over here. And of course, we did various different characterization maths, various different characterization to prove definitely the oxide is getting converted into the metallic part. For example, you can see the nickel metallic peak in the XPS that is being formed over there. So all these chemical character, the structural and the chemical characterization were done in order to prove that we get what we wanted to get. For example, in the XRD, you can see that the peaks related to nickel molybdenum starts to appear in addition to the oxide. So because it was only on the surface, okay, so that it shows that it is getting converted into this after 30 seconds of plasma treatment. And the most important part was that what kind of electrochemical performances it gives. So electrochemical performances, it can be evaluated by different techniques. So over here, you basically try to see, first of all, what is the over potential of these, different materials. So for example, and you have to benchmark against the platinum electrode, because the platinum is supposed to be the best, and it remains the best even over here. And this was the starting material, nickel molybdenum oxide, and then we used different plasma treatment, 15, 60, and 30 second. So we found that the 30-second treatment was the second best after the platinum carbon, and which is seen over here, because you see the over potential, which is listed over here, is the second highest after the platinum. Platinum can the over potential for platinum is only 45 millivolt, whereas for after 30 seconds of carbon plasma treatment, the over potential was 76 millivolt. Whereas if you don't treat it with the carbon plasma, the over potential was almost like a half a volt, about 406 millivolt. So you see a drastic improvement in terms of reduction of the over potential from 406 to about 76 millivolt only. So that is what it caused. And also the chemical kinetics, the reaction kinetics is actually is demonstrated by the Tefal slope. Tefal slopes, the smaller it is, the better it is for the reaction kinetics. And we found that the Tefal slope value was one of the best, of course, after the platinum. So we were able to get very nice material just after 30 seconds of carbon plasma treatment. And then we did the stability analysis, and then it was found that the electrode is stable even after 36 hours. You take this, the current density versus the potential curves over there. So you can see that even after 12 hours, 24 hours, or 36 hours, the curves are almost overlapping with each other. That means the target did not deteriorate. It remains as stable as possible. And you can also see that the over potential was also not changing much. It is still increased a little bit, but well within the limit, quite stable. And one of the reasons why it remains stable was of this carbon layer protection at the top of this material that you see over here. Even after 36 hours, these are the images which are taken after 36 hours of continuous use of HER reaction. And you can see that the metal nanoparticles are still decorating our nanowires, and the carbon shell is still intact. So this structural integrity and better performance is because of this particular property of having this carbon shell coverage of our material. So that is what we demonstrated, that instead of doing a chemical method, if we just use a carbon plasma, we were able to form a very stable electrode, which has the significantly improved electrochemical performance as compared to the pure oxide nickel molybdenum oxide materials, because of the nanoparticle decoration, metal nanoparticle decoration. So that is the first work that I wanted to discuss. The next thing that I want to discuss or show is the another work where we are using this vertical graphene nanotube arrays for the sodium ion batteries. Now, as we know that the lithium ion batteries, of course, these are the right now, the backbone of this energy storage industry. But as we all know, lithium is only available in, Latin American countries, the so-called Andes countries, which actually have, I think, more than 80 or 90% of the lithium reserves of the world. And the lithium reserves that we have will not last more than 80 years. That means we have to find an alternative source. So next to lithium in the same chemical group, we have the sodium. So people want to develop now the sodium ion batteries, and that is where the big research is also going on. They are already there. Some of them have started commercializing them. So sodium, why it is sodium? Because sodium is much more abundant compared to lithium. So that's why there are lots of efforts that are going on in this direction. Of course, there are some problems that the size of the sodium ion is much bigger than the lithium ion, so it's not so easy to so it's kinetics, it's a bit slower. And that is, therefore, we need to work with the more open structures. So that is why in this case, we are working with the graphene nanotubes for the sodium ion storage. Now, what was done in this case, like what is shown over here, this represents the overall schematic. So over here, our starting material was the copper oxide nanowires. And these copper oxide nanowires, they were then treated with the carbon plasma. What this carbon plasma was doing initially, of course, there are some nanoparticles were deposited, but as you increase the plasma processing duration, by the end of 10 minutes, we start seeing the vertical graphene growing on top of them. So the morphology changed from the small little nanoparticles to more dense nanoparticles. And finally, when the time is much larger, then you can start getting the hierarchical vertical graphene. So it does two things. It was the hierarchical vertical graphenes were growing on top of this copper oxide, but it was not remaining copper oxide because this carbon was acting like a reductant as well. So copper oxide was getting converted into copper. And once it is getting converted into copper, it is very easy to remove it. You just treat it with the chemical and you can remove the copper. And therefore, we can get a freestanding hierarchical vertical graphene. And that is what was done. So this shows the 10-minute carbon plasma treatment. And you can see over here, these are the XRD graphs. We only see the peaks related to copper over here and the copper oxide peaks, which are labeled over here 002. These are the copper oxide peaks. So these are the copper oxide peaks these are gone, and only the copper peaks these are all copper peaks. And also because this is treated with carbon, you can start seeing the peak at 24 degree related to carbon. That is what you start to see. And then once it is getting converted into carbon, then you can, copper from copper oxide, you can remove that. And this approach is universal. It's not only work for copper oxide, it also works for other materials like nickel sulfide, nickel oxide, cobalt oxide. It works for all these materials, and we tested that and we proved that we can get those. So now what we did, so that is the first step. That means from the copper oxide nanowires, we got the freestanding hierarchical vertical graphene. Okay, that is what we got. Then after we got this vertical graphene, what we wanted to do, we wanted to coat an active material on top of that. So we use PLD then to grow MOS2 on top of that, because that is considered as one of the good material for this kind of sodium ion storage. So we use PLD to deposit this on top of this vertical graphene, and that is what we are calling as MVGT over here. And that's what we did. And this was proven. So this is what you see. After you remove the copper, these are the freestanding vertical graphene. The graphene growth direction is seen in this TM images. And this is the EDX, basically in the TEM, where you see molybdenum everywhere. After the PLD based, you see MOS2. So because MO and S is there, carbon is there as under the beneath surface, and these are those structure of those vertical graphenes that we see. And then we did all sorts of characterization, and let me not go into the details of that, but let me guarantee you, we got what we wanted to get in terms of the structure as well as the chemical composition. And that is what these various tools like Raman spectroscopy, XRD, and we get the right phases as well as the XPS demonstrated. Now, one of the most important result is actually displayed over here. And what it shows is that when many other people, they have tried something similar. They did not use the plasma-based method of this vertical graphene, hollow tubes of vertical graphene that we created, but they have already used reduced graphene oxide with MOS2. They have used carbon nanotube with MOS2. They have used carbon nanoflakes with MOS2. But most of them, their capacity retention was quite unsatisfactory. Even just after 20 cycles, their capacity was reducing by like 83%, or 84% after by 80 cycles, or 62% after 100 cycles. So that means the structural integrity was not good. Their material was structurally disintegrating, and therefore the cyclability reduced a lot. Okay. And also because of the aggregation of the material that was happening in those materials, that is what was reported. And there was a lower conductivity in these materials. So that's why they were not giving good results. Now, what happened for our material is, that is what I want to highlight. So our MVGT, that means this vertical graphene with MOST coated over that, even after 800 cycle, you see what happens. Our capacity drops from, first of all, our starting capacity was higher. Okay. And the capacity only drops to 513 even after 800 cycles. That is a high capacity retention of 92%. And when we tested it at the higher current, that is at the lower current, but we tested it even at the higher current densities of 20 ampere per gram. And we were able to demonstrate all the way up to 3000 cycles. That is this curve. This is showing at 2500. So it did not decay too much. It was still demonstrating 88% of retention. So that shows the excellent performance of these battery materials, sodium-ion battery materials, using the carbon plasma treatment that was developed using the methods that I just described. So using carbon plasmas. So this paper was published in Energy Storage Material in 2019. So let me now move on to probably the last part, and I think because after that I will stop. And this is about the most recent work that we recently published in 2021. And over here we are basically looking into using the alloying mechanism, using the SNO2 as an electrode. Of course, you can say that this is an oxide. How come it goes under an alloy mechanism? It basically is that this SNO2 gets reduced into SN, and then that SN goes and forms the alloys with the lithium ions. That is what we use, and that was what was proven by looking at the chemical kinetics. So as I mentioned, that transition metal oxides, they are very appropriate for anode materials, for the lithium-ion batteries, because of the reasons that I mentioned. But I mentioned that most of these oxide materials, they suffer from the low conductivity, and therefore most of the people, what they do, they either add metals to them, or they make a composite structure with graphene. Like some people have added sulfur and selenium doping of them in order to improve their conductivity. So in our case also, when we thought of working with SNO2, we also did not work directly with the SNO2. We worked with the SNO2 combined with the vertical graphenes that I just mentioned. So in this case, the vertical graphene was used as a starting template material. But then, if you remember correctly, I mentioned that when we go for the alloying mechanism, there's a huge increase in the volume, right? That is what I mentioned last time when I was giving the introduction. So that increase in the volume of this material, because they have the capacity of storing many lithium ion as compared to the insertion mechanism. So these alloying mechanism permits larger lithium ion storage, but that leads into the volume expansion, and that makes this material to perbolize. For example, in this paper, this cartoon I've taken from this paper, it shows that the sulfur, upon lithiation expand, and then this polysulfide formation is there, and then it breaks down. So the methodologies they try to protect is what is called as the core shell morphology, where the sulfur is a core and then you have a shell around it. Over here, there is no separation between the core and the shell. The shell is just on the top of the core. So when it goes under lithiation, it again expands, so the shell gets broken up, and then again the polysulfide formation is there. So core shell morphology is not good in protecting this material. May I request Dr. Khatiwada to please mute himself? Yeah, thank you. Then what we have done in this case, we are adopting this what is called as the yolk shell morphology, where what happens in this case, that between the yolk, which is basically a core now, and the shell, there is an empty space, the void, there is a void over here. So there is a void over here. And that void actually acts like a region where the volume expansion can take place, and therefore the shell does not come under pressure and it does not breaks down. And therefore it can provide the better protection to this core. And that, so what people have done, people have already using this yolk shell morphology, but when they do what they do, they use a chemical method and then they coat. So on the top of the core, they will have a layer of a sacrificial layer. And this is called the sacrificial layer. This is the sacrificial layer that they have. It can be of silica, SiO2, or it can be sulfur, like what is mentioned in the paper. And then they have the shell on the top. And then they dissolve this layer. So this layer is then dissolved using the chemical methods. And therefore you can get then the void over there. Now in our methods, that what we have used the plasma-based method without using any sacrificial layer. And I will explain how we have achieved that. And that's what the beauty of this carbon plasma is over here. So what we did, as I mentioned, we are using, first of all, tin oxide as the material which we want to work with. But then in order to improve its conductivity, we grow them on the vertical graphene. So first of all, we took the nickel foam, and on this nickel foam, we use the CVD method to grow the vertical graphene. So we get a three-dimensional vertical graphene structure. And then we use, then we grow the SNO2 on top of them, SNO2 nanowires, the tin oxide nanowires. So now these tin oxide nanowires are, intertwined with this vertical graphene structures. Now this tin oxide, then what we did, we subjected it to the carbon plasma. So the carbon plasma was bombarded on this tin oxide. So what it does two things. First of all, once again, we start to get the vertical graphene growth. So we see HVG, that means hierarchical vertical graphene growth on this tin oxide. So tin oxide becomes like a template and the vertical graphene starts growing on top of it again. But at the same time, the tin oxide, because it is being treated with the carbon plasma also, starts to convert into tin. So it gets reduced into tin. And that tin we remove by the chemical method. So you see over here, so we use this chemical to remove the tin part. So now we have the core, which is tin oxide. And then we have a void because we have removed the tin by chemical method. And then we have the graphene shell on top of that. And that is what you see in this diagram, schematically as well as in reality using the TEM image. So this is the as-grown tin oxide nanowire. Then you treat it with a different duration of plasma. When you don't treat it with any plasma, there is of course no void formation. When you treat it only with 30 seconds of plasma, then a 10 nanometer carbon layer is formed on top of that, basically the vertical graphene. But there is no void over here. You don't see a free space. You increase the time duration to 90 seconds, then 180 seconds. You see 180 seconds now you start to see over here. So the central part is now getting reduced in size. You see this one is basically tin oxide is getting converted into tin, and then we are removing the tin by chemical processing of it. And then we have this carbon shell on top of that. And this is very beautifully seen in this particular image, which is basically about the 300-second treatment, 5-minute treatment. And where you see a nice tin oxide in the center, and then there's a carbon shell on top of it. And this was tuned in such a way, I mean, the duration, the selected luckily was like this, that the radius was actually 1.73 times, and that can take place of 300% of volume expansion in this case, which is what people have reported for tin oxide nanowires. So we were able to make a very precise void formation using this plasma method. And of course, if you do too much of plasma processing, then the entire tin oxide is gone. You see in this one, there is no tin oxide in the center because the entire tin oxide was converted into tin. And when you treat it with the HCl, then the entire tin was gone. So that is what we did not want. We still wanted tin to be there. And then once again, we used several characterization tools to verify what we are getting is indeed what we wanted to get. We are getting the yolk shell structure. We are getting the materials in the right phase, with the right stoichiometry and all that. And I'm not going to go into the details of those results, which are basically seen in this. You can read the paper. What is important is this slide. So this and the next slide. So what we see over here is that if we just use, so we have our standard was the graphene flake with tin oxide without any carbon plasma treatment. And then the second one is the one with the carbon plasma treatment, where we have the graphene flake below, then tin oxide, and then hierarchical vertical graphene on top of that. Okay, after we remove this. And we notice that this material, the one which we grow, it provided much better discharge. Yeah, it provides much better current densities, as you can see from here, as compared to this. There is almost like a 25% increase. And also you can see when we do the electrochemical impedance spectroscopy, it shows also better result over there in terms of course, smaller circle, semicircle, which basically means its resistance is smaller, which is the value which is calculated and shown over here. So that means its charge transport properties are better. And this is the chemical reaction, which basically shows that the acid which is basically obtained from this. Of course, I'm not expert on that. Some electrochemical chemist in our group, he was able to highlight what kind of mechanism is going on. So tin is being formed, which actually do the alloying with the lithium and then forms this lithium tin over here. The most important result is highlighted over here in this slides, which actually tells the performance of this. So if we don't do a carbon plasma treatment, that means it's only the graphene shell with the tin oxide, then you can see the starting capacity, which is the most important criteria of quantifying the your lithium ion battery. The starting capacity is about 450 or something like that. And then when you cycle it, it drops very fast. Within 100 cycle, you see, within 100 cycle, the capacity drops very significantly and it gets stabilized. But then the value is coming down to somewhere around 100 milliampere hour per gram. Whereas our carbon plasma treated SNO2, where we have a yolk shell structure, we did not have a drop, rather it increased initially and then gets stabilized at much higher capacity. Starting capacity is high 654 and it gets stabilized somewhere around 783 with 115%. So capacity retention in this case, previously all the numbers I was showing that was they were dropping to 80%, 90%, 70%, but now we have an increase over here. And there is a reason for that, which is explained over here. It basically because there is a volume expansion together with the protection by the carbon layer. So we have more material or the more sites that are available now for this lithium ion storage, and that improves its actually the lithium ion retention. So this is another fantastic result that we got, and this is published in 2021 in the Nano MD. So basically, I think I will stop over here. As I mentioned, we also did the work on nitrogen plasma. I have another 15 slides over here for nitrogen plasma, but that will take another half an hour. So I don't think I will go into the details of those. And I'll just maybe summarize go to my last slide over here. Yeah, in fact, those nitrogen plasma work that which I did not cite over here. These two papers are among the top 1% Web of Science cited paper, both listed for consecutively last 5 years. I think only one of the paper went out this year, but one of them has 364. The other one has over 500 citation in last 3 years. So these are our highly cited paper. So what I wanted to highlight is that the future, of course, belongs to hydrogen economy, and we need to shift away from the carbon economy. And low temperature plasma tools, they actually provide an excellent, plasma tools to synthesize nanostructured materials for energy storage and conversion materials. This is pretty simple systems to use. These battery related work is not very difficult, and that is one of the reasons why many people work in this field. And that is why one of the reasons that when you work in this field, your citations are large, basically because not many people are working over here. Some basic work can be done in any laboratory. You don't need extensive equipment, but of course you need to have access to maybe some central facilities where you can do maybe some XPS or TEM, or you can work your collaborators to do those parts. But other than that, battery performance analysis and electrocatalysis performance analysis, it's something can be done in very easily in even undergraduate chemistry lab. So that's not a big deal. So I will strongly motivate some of the researchers over here to think about this kind of direction to work into, which is basically high impact research because of its uses. Thank you very much for your attention, and I will be happy to take up questions.
Thank you very much, Professor. Scintillating lecture for more than an hour. Thank you very much.
Sir, very thanks a lot. Very nice presentation. Audience, if you have any question regarding this talk, you can raise your hand.
Dear participants, if you have any questions, you can raise your hands or you can post your questions in the chat box.
Madam, chat is disabled.
Yeah, now it is enabled, sir. Now it is enabled. So you can ask the question. Please raise your hand or directly you can unmute yourself and you can ask the question.
Yeah, hello. Can you listen me?
Yeah, hi, Ken. I can listen.
Yeah.
I can hear you.
How are you?
Fine. Good.
This was a wonderful and informative talk. I am from Pakistan. Dr. Jalil is here.
Dr. Zalil.
Yeah.
Welcome.
Actually, I am working on battery material by using a DFT. Can you suggest and collaborate? How can we deal this by simulations or in computational methods? Is it easy for us or difficult?
I think working on DFT is good. In fact, we have a paper in advanced material, which I did not discuss over here. It's this paper. I don't do DFT, but this paper, which is listed over here, this paper number 4, you can go and read this paper, which is basically again a work done by us on using this graphene SNS bundles, tin sulfide bundles for very high lithium ion storage. And in that, we were supported by some DFT calculation by a group in China to support our experimental results. So definitely DFT people are very useful for this kind of research, and you can work with them. And Dr. Jalil, which university are you from in Pakistan?
I belong from Khaja Fareed University of Engineering and Technology, Ramya Khan.
Oh, okay. So I have a friend in this government college, Faisalabad, Dr. Izaz Ahmed Khan. I have more than 20 papers with him. And recently I wrote a research proposal. He is also very interested in doing this battery kind of a work. So he was here in Singapore for 1 year under your HEC program, your University Higher Education Commission program. And he went back and he just got a very big project about 2 crore Pakistani rupees on battery related work, where I am a collaborator. So I'm helping him to develop those facilities there in Faisalabad. The project was approved only last month, but you can contact him. His name is Izaz Ahmed Khan.
Izaz.
Izaz, yeah, Izaz Ahmed Khan.
Okay, that's nice to listen for that name. Basically, in government university, I have 4 to 5 my class fellows working over there.
Or you can contact Professor Riaz, or you can contact Professor Riaz Ahmed from Government College Lahore.
Okay.
Yeah. So
okay, it's nice.
So he's also working on this kind of similar field.
Okay, it's nice to see. I want to learn which software and which paper you are talking. Maybe I want to know about the software which are using, and that's material for computational calculation.
Yeah, so as I mentioned, I don't do the DFT calculations, so I have no idea. Our collaborator did that. So
okay,
yeah.
Okay,
and in
nice,
the
nice.
paper, I think you will find the details in the supplementary information there. The details should be there.
Okay, thank you very much. But it's
Welcome.
very nice. It's very nice, and how impact factors, journals and materials. I am happy to listen to your talk. Thank you.
Thank you.
Professor, one more question in the chat box, Professor.
Yes. Yeah, I saw that question. So how about the stability and the number of cycle using carbon plasma?
Yes,
So
sir.
yeah, that is what I was highlighting, that that the stability of the materials that we got after the carbon plasma treatment was excellent. And one of the examples that I gave was in this slide. Can you still see my screen? Can you still see my screen?
Yes, sir. Yes, sir.
Yeah. So you see the stability is reflected over here. As you can see in this discussion over here, as I mentioned, that the stability of other materials used by other group members which were not using the carbon plasma was not much. The cyclability was not more than 100 cycle for this particular MOS2, which was grown on the carbon-based material like the reduced graphene oxide or CNT or other things. But we demonstrated the stability all the way up to 3000 cycle, as I mentioned. So the stability definitely is improved a lot using the carbon plasma. And I told you the reason for that. The reason for that is that this carbon plasma, as you see in this graph over here, this images over here, the carbon plasma forms a shell. It forms a nice shell on top of your material, which while remaining permeable to the lithium ions, protect it. Okay, so it provides a better stability to this material, and therefore it can be used for much longer duration. I hope that answers your question, or is there anything else that you wanted to know?
So one more question is there, sir. How the presence of extra metallic ion in the electrode affect the overall supercapacitance?
Sorry, which question?
First question, Professor. How the presence of extra metallic ion in the electrode affect the overall supercapacitance?
Okay, for supercapacitive related work, most of the work that I displayed over here was basically respect to lithium ion batteries or sodium ion battery. We have done work related to supercapacitors, but over there we did not work on the metallic ions or so on and so forth. It was basically using the MOS2 on top of the vertical graphene. So we did not do any metallic ions in this case. So I'm not in the position right now to comment on that supercapacitance value. But what we noticed that when we have this MOS2 directly without having any intertwining through the vertical graphene, the supercapacitance performance was less, and it improved by 3-fold. I'm not showing that paper. It's our paper in Electrochemica Acta. And it was increased by, I think, 3-fold times when we use it with the vertical graphene. But that work did not involve any metallic ions. So I cannot comment on that.
And one more question, Professor. That research scholar is doing research on CeO2, in which XRD graph he found that 6-degree deviations for doped samples than pure cerium oxide nanoparticles. Is it possible, sir?
6 degrees is too much. Maybe there is some I don't know, there may be some instrumental error. Of course, with the doping, what you expect, because of your change in the despacing, your peak, XRD peak will shift. But I don't expect it to shift it by such a great amount. Typically, the shift are, I think, less than a degree, half degree or so. So he has to see whether it is really a shift or is it some new phase formation. So doping can also lead to a new phase formation, and that may be altogether a different phase. So what I would suggest that a person should do some Rietveld analysis, try to fit them with the phases that he thinks are there, and then try to think about some of the impurity phases that can be formed, and whether C can get with confidence the Rietveld fit, and then he can analyze whether it is a new phase formation or whether it is just simply the lattice under stress due to doping. So I think it is a new phase formation that probably has taken place over there.
One more question, Professor. Can we use silicon nanowires? Yes, ma'am.
Sir,
Yes,
can you spare your time, or share your mail ID?
Sorry?
If time permits, you can answer, sir, or else we can, if you give permission, we will share your mail ID.
Yeah, they can use my email ID, but it is better to ask the question now, because sometimes we are so occupied.
Okay.
Email replying, it takes more time rather than physically explaining,
Yes. Madam, please ask.
I have not taken my lunch. I'm feeling very hungry, but it's okay.
So sorry.
It's okay. Yeah, what is the other question?
Can we use
sir,
silicon?
Madam, 2 மணி அங்க.
Okay, I'll stop with this, ma'am. Can we use silicon nanowires in the place of SnO2 nanowires, sir?
That will be fantastic, because what I mentioned is that the silicon actually has the much higher dissolution lithium ion storage capacity. You remember the table that I showed, the lithium, and which is, let me show you again. So that lithium can there is about it forms SiLi 4.4. That means lithium has much higher capacity to store this, and I think it will be very good or very interesting if the lithium silicon nanowires are treated with carbon plasmas, so that carbon plasma will form a shape on top of that, and we have to think about how to convert this silicon into yolk shell structure. Okay, we started with tin oxide, and then we use the carbon plasma to convert the top layer from the tin oxide to tin, and then we remove chemically. In case of silicon, I think the top layer of silicon can also be oxidized, but I think removing silicon is a problem. So forming a yolk shell structure will be difficult. But if we just think about it, just protecting it only by the carbon, I think it will still give improved protection by carbon plasma treatment. So I think silicon nanowire can be used. We actually wanted to work on that, but I did not have the facility to grow silicon nanowire. We were trying using PLD, but we were not able to succeed. So that will be good. If you have those silicon nanowire, you can definitely try this.
So, thank you, Professor. Due to time constraint, we are ending with this. Thank you, Professor. Thank you so much. Now I request Dr. K. Subramaniam, sir, Assistant Professor, Department of Physics, to propose vote of thanks. Sir.
Yes.
Thank you. I will stop sharing now.
Yes.
Very good morning, all. On behalf of the management and Department of Physics, SRM IST Ramapuram campus, Chennai, my heartfelt thanks to Dr. Rajdeep Singh Rawat, Professor and Head, Department of Natural Sciences and Science Education, Nanyang Technological University, Singapore, for delivering a wonderful presentation on plasma processing as a novel tool for high performance electrode material synthesis for high energy storage and conversion devices. Sir, we are really thankful to you for your contribution towards this STP session in your busy schedule. I know that today you have given another keynote address in the United States of America in a conference. So
no, it was not a keynote. It was just a normal talk.
Okay, so really it's an interesting topic, sir, and the presentation also very wonderful. My sincere thanks to our chairman, SRM Group of Institutions, Director, Dean, ENT, Vice Principal, Academic and Administration, SRM IST Ramapuram campus, for your support to make this event to be a successful one. Last but not least, thank all who already actively participated in this session. Thank you very much.
Thank you, Professor.
Thank you. Thanks a lot, Professor.
Madam, feedback from Andrige. Feedback.
Dear participants, feedback form has been posted in the chat box. Only fill it.
Jayalakshmi ma'am, please mute, ma'am.
Yes, ma'am. I'm muting. Dear participants, feedback link has been posted in the chat box. Kindly fill it.
Professor.
Yeah.
Thank you, Professor. You can.
Thank you.
Leave, Professor.
Thank you, Professor.
Thank you. So I'm going
Because
to leave
of
the
us
session.
today
Thank you.
delayed lunch for you.
Oh, no, no, it's okay. It's okay. Fine. Thank you. Thank you.
Thank you so much.
All
Thank
right.
you so
Bye-bye. Bye-bye. Have a nice day, everyone.
Thank you, sir.
Bye.